On this episode of Nova Science Now, physicists are gearing up for a landmark event.
It's a big step. This is a big time.
They're about to turn on the world's largest machine.
We may find things which nobody has ever thought of.
In their quest to find out exactly what the universe is made of.
It's just a voyage of discovery.
Mind-boggling.
Mind-boggling and mysterious as the synchronized movements of flocks of birds, schools of fish, and even crowds of humans.
Behavior of the whole is more than the sum of the parts. And that's the flag for emergence.
Could the science of emergence unlock the secrets of intelligence? Even the origins of life itself?
This whole concept gives us a new way of thinking about the universe.
And more on this episode of Nova Science Now. Some believe the sleeping brain could lead us to real insights.
We all know about sleeping on a problem. And sleeping on a problem is when you have a lot of new information and don't know what to do with it. And you can't decide how to interpret it. And so you say, let me sleep on it. And with remarkable success rates, you can wake up the next morning and have an answer to a problem that you couldn't find the answer to the night before. And that's all about processing information, processing memories in the brain.
Watts of electricity to get the thing to work. Well, a bunch of real scientists have been working for years on one giant experiment, trying to create exotic particles that haven't existed in the universe for 14 billion years, back to the Big Bang itself. Physicist and correspondent David Work reports that in a way, it is a giant time machine. Just like in the movies, it's all about energy.
You'd never guess that hidden beneath these French mountains, an army of workers is underground, constructing the biggest and most complex machine on Earth. It's a project that's got physicists around the world brimming with anticipation.
It's a big step. This is a big time.
We may find things which nobody has ever thought of or told us before.
It's a real adventure, because we don't know if it's going to work.
The goal of this giant construction project is nothing less than to find the basic building blocks of the universe.
The basic quest of particle physics is, what is the world made of? Do we know everything? Do we know all the constituents of matter? Do we have them all?
Scientists have already found a whole carnival of subatomic particles that make up the universe.
List some names.
Matter as we know it today.
There are protons, neutrons. That's what we're made of.
The top quark,
Bottom quark
the up
and the down quarks.
charm quark, the strange quark.
There was a time they just named everything something silly.
There are pions, kaons,
W bosons, Z bosons.
5 different upsilon particles, lambdas,
Gluons for the strong force.
omegas, sigmas.
Muons.
Who ordered that?
And my favorite particle is the tau.
This panoply of particles is called the Standard Model, and it's our best picture of what the universe is made of. But as dazzling as it is, we know that the carnival is incomplete. There have to be other hidden particles out there, and we need a new experiment to find them.
Normally, physicists don't get to ride in helicopters, but today we want to see the world's largest experiment. And up here is really the only place you can get a sense of the scale.
Below me is the construction site at CERN, a particle physics lab. The new experiment is so big, it stretches from the mountains in France across the border to the Geneva airport in Switzerland. That's because the main part consists of a circular tunnel 16 miles around. The tunnel is home to the world's biggest, most powerful particle accelerator ever, called the Large Hadron Collider, or LHC. Because it's so big, the LHC will let us probe deeper into the stuff of the universe than we've ever gone before. this tunnel is being filled with giant electromagnets.
And in fact, you can see some of them on the ground right there.
This is my stop. Each tubular magnet costs close to $1 million, and the LHC will need more than 1,600 of them.
So what is this?
This is the magnet. This is the magnet which is inside this big blue tube.
Okay.
The magnets are designed to keep those tiny parts of an atom, called protons, flowing in a narrow beam through the tunnel. When they're all connected together into a ring, the magnets will create a 16-mile racetrack for protons.
In the ring, the powerful magnetic fields force the protons to go round in a circle. And each time they go round, they get a little kick from an electric field. So they go faster and faster, until eventually they're traveling almost at the speed of light.
In fact, the particles, they are traveling in these two tubes. In one of the tubes, the particles are traveling in one direction, and in the other tube, in opposite directions.
So there's actually two beams of particles going in opposite directions.
Yes.
One beam going one way and one beam going the other way.
Exactly.
And there's two beams because you're going to collide them.
Exactly.
This is a technique that's familiar to physicists. A proton traveling close to the speed of light, although absolutely tiny, will carry a lot of energy. Two of them traveling in opposite directions will carry twice the energy. Make them collide, and most of that energy can be released in a tiny but powerful explosion. With enough energy, the explosion should create fundamental particles that we've never seen before. If that happens, it'll be in a tiny region smack in the center of a vast underground cavern.
This is one of the 4 places around the ring where the two beams will actually collide. One beam will come from a tiny beam pipe through the middle of that hole over there and fly over my head. And the second beam comes through that hole over there, and high up over my head in the middle of the cavity, the two protons will collide. Now we're colliding two tiny little protons. Why do we need this vast cavern to find out what happens?
Well, in order to detect if any new particles have been created in a collision, researchers have to fill this cavern with some of the most complex scientific instruments ever created. The one here is called CMS.
This is one end of the vast CMS detector. The whole detector consists of a series of these plates, each one of which is instrumented with thousands of detectors you can see up here. As we move down, you see a large number of these which will all be slid together to make the final detector. No space at all is wasted. This big hole looks like a hole in the detector, but in fact, the hole in those detectors is filled by these detectors.
Different detectors pick up different kinds of particles. And sandwiched together, they'll create a single enormous cylinder which completely surrounds the point where the protons collide. That's important because as the particles fly away from the collision through the detector, they'll leave tracks which form a kind of fingerprint. It's by analyzing these fingerprints that scientists should be able to tell if a new particle was briefly created at the moment of collision.
That's why the experiments are hugely complicated. They have to identify all the things that come out of two protons that hit.
The LHC experiments are by far the most difficult that have ever been done in high-energy physics, and maybe any experiment.
In fact, the experiments are so complicated, it takes physicists from dozens of countries to pull them off.
I'm from Switzerland.
I'm from Belgium. Sono italiana, Toscana.
France.
Japan.
Austin, Texas.
Russia. The UK.
California.
From Senegal.
New Jersey.
Colombia. India. From Bombay.
From Germany.
Argentina.
I'm from Togo, West Africa.
I'm from Brazil.
And I'm from the Czech Republic.
You meet people from all over the world. You talk with them, you get their point of view, exchange ideas. They all tend to be physicists, so it's not that wide, but I find that's exciting. If the rest of the world worked the way we do, we'd have far fewer problems.
One problem they do have is analyzing the vast mountain of data that the LHC is going to produce. Because when it's running, it'll create about 1 billion proton collisions a second. And it'll be running 24/7.
We get 40 million megabytes of data created every second.
40 million megabytes,
Right.
40,000 gigabytes, or that would be 1,000 large disks for your home computer every second.
Yes, it's mind-boggling. The amount of data that we'll be generating in 1 year is 10 times bigger than all the World Wide Web stored data.
In fact, the World Wide Web was invented here at CERN to analyze the results of earlier experiments. But the LHC has so much more data, it will need the power of the Webb's successor, something called the grid. Using millions of computers around the world, the grid will turn high-speed computing power into just another commodity, like music or telephone service, that someday soon everyone will be able to buy online. It's all part of a quest to understand the world in minute detail. One mystery scientists would love to solve is why some of the particles now whizzing around the universe have mass.
The fact is, from a physicist's point of view, from a philosopher's point of view, from an observational point of view, mass is actually quite mysterious.
In our best theory of matter, the Standard Model, all the really fundamental particles are like photons, the particles of light, in that they have no intrinsic mass. But we know that objects in the real world have mass, and scientists know that particles like protons and electrons also have mass. So where does that mass come from?
Why do particles have different masses? And why do they have mass at all? Mass is not something that emerges naturally from a theory.
We basically do not understand why some particles got mass and others didn't. What happened? What gave mass?
The leading idea for explaining mass is something called the Higgs field, a field which we believe pervades all of space and which the fundamental particles interact with.
The Higgs field is like cosmic cotton candy. It sticks to everything. And according to this idea, it's actually that stickiness that gives particles their mass.
If the Higgs field, along with a Higgs particle, really exists, then the Large Hadron Collider should find it. And that would be a triumph for the Standard Model. But since the LHC will take the particle hunt to a whole new level, many physicists are hoping it will uncover types of matter we've never even dreamed of.
The best case in my mind, we do not find a Higgs particle, and we find a whole new set of new particles.
I don't really care what we find. I just want to go off there and look at something and see something no one's ever seen before. That's what motivates me.
It's just a voyage of discovery. It's looking out into the cosmos and trying to see where we fit in it.
Many people think that the laws of nature and the universe tell us that everything breaks down. Things fall apart, energy wanes, living things grow old and die. Yes, we have some good laws which explain all that. But what about the emergence of life? What about the complexity of life? Where do they come from? Are these rare, miraculous developments? Or is this kind of complexity inevitable, following natural laws we just haven't figured out yet? Correspondent Carla Wohl went looking for the answer.
It is mysterious how a flock of birds or a school of fish move as one with such grace and coordination, as if there's one brain behind them all, or an invisible force at play. An explanation may be found in emergence, a science that tries to explain complex patterns and behavior that arise in the world around us. Some believe emergence may reveal more than just how birds and fish do this, but how we think and how life itself began in the first place. But while many of science's mysteries long have been explained, gravity we predict with Newton's laws of gravity, and magnetism through Maxwell's laws. Things like this remain largely unpredictable.
Emergence, when you first see it, seems mysterious. But that, if I go back and read the papers at the time of Maxwell, electromagnetism seemed very mysterious too.
Let's start with what we do know about emergence. It's an order we might not expect to see. Usually where there is order, there's a leader, a conductor of an orchestra, or a general with his army.
Orders come from the top and
they go down.
Top-down order, where you have one brain controlling the functions of the entire group.
A leader at the top and many who follow down below. It's just how we expect things to be. So who's in charge here? Him? No. Him?
There's no conductor, there's no general, there's no leader, there's no director that's telling every fish where to go.
Well, then what about these birds?
There's no one in charge of the birds either.
So if the order isn't coming from the top down, where is it coming from?
The organization comes from the bottom up. So at the bottom we have these things that are following their own sets of rules, often fairly simple. One is to go in the same direction as the other guys. Another is don't get too close, but don't get too far from my neighbors.
And perhaps the most important rule? If someone's coming after you, get out of the way. From these simple rules, very complex patterns can spontaneously emerge.
What we see is a pattern emerging from the bottom up.
And so it came to be called emergent complexity, or simply emergence. Of course, different creatures have different rules, but whether ants, or wildebeest, or this slime mold,
the behavior emerges from the actions that are controlled by the rules. And the behavior of the whole is more than the sum of the parts. And that's the flag for emergence.
And you might not have noticed it, but it's not just seen in animals.
Similarly with crowds, there are no leaders within certain types of crowds.
Crowds of people? We do it just like the birds and fish?
Movement is happening at a very much subconscious level. You don't think about how to walk, you just do it.
Keith Still studies the emergent complexity in crowds. He says these people crossing the street have no idea they're part of a larger pattern.
As if they're following each other in long conga lines. What happens is that the first individual that finds a gap is being followed by those people that find it easier to follow something that's moving in roughly the right direction than it is to carve their own path through the crowd.
So emergence happens with all kinds of living things that move in groups.
It can be a crowd, it can be a flock of birds, a school of fish. These are all emergent phenomena when you're getting a large-scale order out of a small-scale interaction.
But emergent complexity can be found in non-living things as well.
Anything I know that exhibits emergence involves a lot of, we might call them agents, a lot of individuals or parts. We could call them parts.
John Holland's first experience with emergence came from some fairly unsophisticated electronic parts that came together to create something almost intelligent. And he saw it a half-century ago with a game of checkers.
You used to look at this as child's play, right?
Yes, I did.
I believe it's your move, too, by the way.
All right.
What changed your mind?
What changed my mind was my encounter at IBM. This was in the early 50s. I was busy at that time simulating neural networks.
Meanwhile, a co-worker, Arthur Samuel, was doing something else.
He programmed the machine to play checkers, and I thought, well, what he's doing is interesting, but that isn't anywhere near as deep as simulating neurons.
It's checkers,
yeah,
right?
It's checkers.
As it turned out, Samuel had achieved something far deeper than anyone at IBM expected.
He programmed the rules, and the machine would move according to the rules.
Not only was the computer following the basic rules of checkers, it had another set of rules as well, a strategy to favor moves that might lead to victory.
Simply by its experience with him and other players, it favored better moves than he did. That machine learned well enough that it could actually beat Samuel himself. With this learning, I have emergence.
It was emergent because when the computer followed simple rules, something as unpredictable and complex as learning emerged. Something until then only living things could do. 50 years later, computers really don't seem to have come all that far.
Good evening, Dave.
How you doing, Hal?
2001 has come and gone.
I've wondered whether you might be having some second thoughts about the mission.
Computers were supposed to be having conversations with us, thinking for themselves. So why can't they? Holland says that's because there's another important factor in emergence to consider. Complexity depends on how connected the parts are to each other.
Compare the central nervous system, our brain, to a computer.
There's a major difference. Each element in a computer, each transistor, contacts at most 10 other elements. But in the human brain, each individual neuron contacts 10,000 other neurons.
So the sheer number of neurons in our brain, as well as the number of connections between them, is what makes our brain so much more complex than a computer.
I've got billions of neurons, and each one touching 10,000 others. So we get the emergence, and maybe some of us believe that consciousness is one of the emergent phenomena here.
Consciousness? Could something so complex spontaneously emerge from individual parts following simple rules? It may seem counterintuitive. Many of us think that without a leader or a plan, things become more disordered with time.
Our intuition about the world is that things deteriorate. We get old. We die.
Buildings crumble. We expect decay.
This is the increase that's inevitable in the universe of disorder.
But if order can emerge from disorder, could we actually expect to see something as complex as life itself emerge?
Many of us believe that life follows inevitably as another emergent complex phenomenon.
Bob Hazen, an astrobiologist with the Carnegie Institution, is trying to find out if life on Earth emerged from simple molecules arranging themselves into something living. Hazen hypothesizes that the right molecules under the right conditions will do this, form increasingly more complex structures. And those complex structures will form even more complex structures, and so on, until finally you get life. To start, he needed a simple molecule. He chose pyruvic acid.
Pyruvic acid is a good proxy for the kind of simple molecule that would have been abundant on the early Earth. It's colorless, it's basically odorless. And you load it into a gold tube, it's like threading a needle. You then seal this up.
Hazen is trying to reproduce the energy of the heat and pressure deep within the Earth.
Typical of conditions that might occur in volcanic zones on the floor of the ocean. Seal this up.
He pressurizes and heats the capsules to 250 degrees centigrade.
It's like a pressure cooker. Emergent complexity takes place in any environment where you have lots of agents coming together, molecules coming together, and energy.
And in a week's time, he's recreated the heat and pressure. The one thing missing is water.
And that's the magic trick. Put it in water, and bingo. Those molecules self-organize into an enclosure, cell-like structures called vesicles, a structure which is essential for life.
So here the agents are molecules. The rules are the rules of chemistry. What emerges is one step closer to something biological, an important first step towards life.
And the origin of life must have been a sequence of emergent steps from simplicity to complexity. You go from the simplicity of volcanic gases like carbon dioxide and water to organic molecules.
Still, a vesicle needs to capture energy and nutrients to grow, replicate, and divide before it can truly be a living thing. And whether these steps are emergent is, for Bob Hazen, the great mystery to be solved.
This whole concept of emergent complexity gives us a whole new way of thinking about the universe, going from the simplicity of the earliest universe to the complexity of the modern living world.
Even Hawking says complexity is the study of the 21st century. Maybe in 20 years, it'll be the standard science for all I know.
Scientists would love to quantify emergent complexity. We'd love to be able to have a formula that told us what systems become complex, how complex they become.
My guess is that we will find some laws that will let us describe some things in these complex adaptive systems, patterns that we can recognize and maybe even make predictions about. And that's the great advantage of Newton, of Maxwell, and maybe someday we'll get our own Maxwell.
Was that voice in the wilderness? Most of us think of the Old West as the stuff of myth and legend and cowboy movies. But the West was made by very real people. And people always leave stuff behind. So, if you're willing to get your hands a little dirty, like the archaeologist in this episode's profile, you might just discover the real story behind the myth, buried in the dirt and the sand.
We're just about there. And this just might be a little deeper. Yeah. Or perhaps it might go down even on the...
Julie Shablitsky is an historical archaeologist with the University of Oregon.
Look, I'm a shot putter.
She's not afraid to get her hands dirty as she digs for the truth. Literally.
Ooh, looks like an alcohol bottle.
Each archaeologist that goes out to a site is looking for a story.
It's a crown cap, though, so what's the middle mark? Is that CG together? I can date that.
Here. A story that will tell them something different about the people who used to live there.
What's the base of the bottle say? An S?
Something that hasn't been known before.
William Franzen and Son, 1900 to 1929. Yeah, I saw that. Milwaukee, Wisconsin. Ah!
So the Holy Grail isn't necessarily an object, it's a story.
Julie brings her passion for her science to what was once the site of a 19th century Chinatown in John Day, Oregon. That's where she's trying to tell the story of the thousands of Chinese laborers who came west in the late 1800s.
The Chinese were instrumental in building railroads. They were instrumental in mining. They made shoes. They were cobblers. They cut hair. They were servants in people's homes. They were cooks. Like all immigrant communities, you really build a country on their backs.
Yet, there are almost no written records from or about the Chinese of that era.
You don't see them documenting their life in journals, and very seldom do you find even letters that went back and forth between them and their families. So you have this gap of what it was like to be Chinese in 19th century America.
Oh, yep, it's a single dose medicine bottle. It's Chinese. Chinese, definitely Chinese.
And what archaeology can do is it can fill in those gaps, it can give the voiceless Chinese that voice.
Julie's love of archaeology started very early. Her first digs took place on the gravel driveway of her Minnesota home where she grew up. By the time she was 7, this self-assured second grader was telling her classmates she had found her life's calling.
Back then, when I thought about archaeology as being a lot of the gold idols with the ruby eyes and mummies and things from faraway land, and I never really realized that archaeology could be in your own backyard.
An idea that grew, along with her, through elementary school into high school. Even the poster on her bedroom door was of an atypical rock star.
Ramesses II is not the average teen idol, but I found him quite interesting.
Today, her interests have gone beyond the idols and icons, and even the physical artifacts themselves.
You found a coin purse.
Oh my gosh, sure enough.
The bottle that you could pick up, the arrowhead that you could hold in your hand and think that, wow, someone made this. That's what really grabbed my interest. But what held it was that when I began to put those artifacts together and tell a story, that was really important.
And that's exactly what Julie helped to do on a headline-making excavation involving one of the great and gruesome stories of the Old West, the story of the Donner Party. The group of westbound pioneers who, because of bad luck, an ill-chosen route, and early snows, were trapped in the California mountains for a bitter winter in 1846-47.
So you had a little over 80 people stranded in the Sierra Nevadas in 2 different camps. In both camps, about half the people lived and about half the people died.
Just what the living did to survive horrified everyone who heard the story. Some survivors in the larger of the 2 Donner Party camps admitted they had cannibalized the bodies of those who had already died.
It seemed that everyone was for sure that cannibalism was participated in by every single member of the Donner family party. I think a lot of people believe that they survived by eating each other.
Julie was the co-leader of a team that went back to the second camp to get a fuller story of what really happened there more than 150 years ago.
We want to know if they cannibalized. We want to know if they didn't cannibalize, how did they survive? How desperate did they become? What did they eat?
Julie's team discovered a buried hearth and a trove of burned and chop-marked bones. She took those bones and did what she's become known for. Julie brought in experts from other scientific disciplines. In this case, forensic bone analysts. Their findings? Those chopped, boiled bones were those of hunted deer and rabbit, of their horses, even dog, but no humans.
These people ate their family dog. They did everything in their power to extract every last nutrient before they did the unthinkable.
Thanks to Julie and her team, about half the Donner Party members at the second campsite were exonerated, correcting the sensationalized stories of the entire Donner Party quickly resorting to cannibalism.
It looks like only several people did participate in cannibalism, and not to the very, very end of their entrapment. So I think that's a real big finding for us.
I think she's something of an emerging star in historical archaeology.
Go!
One of the things that I love so much about Julie, and especially enjoy working with her, is the enthusiasm.
That's way cool.
It's so infectious.
Oh, wait. Oh, my gosh. I think this is a soy sauce. It looks like right on top of this board here is a spout from a soy sauce bottle, a Chinese soy sauce bottle. Yes. There's no doubt what this is. There you go.
She is really there to really help in times when your work is long, hot days and it's frustrating work. She's still like being the cheerleader.
Which in fact, she used to be. She's always been active. The volunteer firefighting, snowboarding kind of active. And she says she's always been a tomboy. But the kind that's never been afraid to wear pink, or to poke fun at herself, or to try something new.
Oh, Susanna. There's both the part of me that can be dressed up and feminine, but at the same time can also be a scientist who likes to play in the dirt. And I've always been true to who I am, and I've always been comfortable with being, I guess, a lipstick archaeologist, if you will.
But make no mistake, this lipstick archaeologist is not someone to be taken lightly. Julie's one of the first archaeologists in her field to discover historic period DNA from an artifact. She excavated this glass syringe from a site in Virginia City, Nevada.
Nowadays, forensics and DNA is a household word, and I wanted to understand what the syringe was used for. I wanted to know who used it. Knowing that it came from a 19th century structure just was not enough for me.
DNA tests revealed that at least 4 people had used the syringe to inject an opiate, most likely morphine.
There were both men and women that used that syringe, and perhaps one of those individuals was from African descent.
And I would never have been able to know that with just using traditional archaeological methods. And one thing we're not finding is there are no women's personal items, and that's because we're in a bachelor culture, really.
She's really good at interpreting history for the public. We have to share our findings with them and make it interesting, not just blasé.
This came all the way from China back in the late 19th, early 20th century, and it's either from a food storage jar or... My goal as an archaeologist is not just to dig up the artifacts, put them in a bag, and put them in a museum somewhere, but to get that out to the public, people that have an interest in and who was here before them.
Julie Szublitsky's commitment to her science is driven by her passion to understand the past, to reconstruct history, one artifact at a time.
Even little bits and pieces from a Chinese trash pit.
This is excellent preservation.
Or DNA from a syringe can be brought together to tell a bigger story.
I feel good. That's a nice complete piece. And you guys
Julie even married an archaeologist, Bob Nyland, an underwater archaeologist with the U.S. Navy.
He's water, I'm land. So he shares my passion. If you really have a drive for something, a desire, this passion that is inside of you, don't ever think, oh, I can't do it. I think it's very, very rare that people take a passion that they have and turn it into a profession. But I think it's completely possible.
And now for some final thoughts on subatomic particles. We learned early in school that there's such a thing as atoms, and that all of matter is composed of them. A little later we learned that atoms, a word by the way from the Greek atomos, meaning indivisible, are themselves composed of even smaller particles, the familiar electrons, protons, and neutrons. Under exotic conditions of high energy, like what's common at CERN and in other accelerators, particles wholly unfamiliar to everyday life pop into existence. But what may be unfamiliar to us is common to the cosmos. Want to find the biggest accelerators of them all? They're out there in the universe. The million-degree cores of stars, the turbulent environments of massive black holes dining on gas clouds that wander too close, or the stupendously hot conditions during the Big Bang. So while physicists probe ever higher energies to understand the fundamental building blocks of matter, those same experiments serve as a probe of what's going on across space and time. There lies one of the most remarkable stories of modern science, how the study of the smallest constituents of matter offers deep insight to the biggest event there ever was, the birth of the universe itself. And that is the cosmic perspective. And now, we'd like to hear your perspective on this episode of Nova Science Now. Log on to our website and tell us what you think. You can watch any of these stories again, or listen to podcasts, hear from experts, or even take our survey. Find us at pbs.org. That's our show. We'll see you next time.